Okay, I'm going to try to run through more examples of motion and velocity to try to make this a little more understandable. So let's picture another diagram where we have a car and it's traveling along in a straight line. But then if I put these dots at further and further times apart, what that's symbolizing is that to get from here to here is about 1 second, here to here is 1 second, here to here is 1 second. So we're getting faster and faster. We're traversing the distance quicker and quicker. So we have two graphs, the xt graphs, and we have the velocity and time graph. Okay, so at this point right here, at A, we have a certain speed already, so I'll just put that right there, A. At B and C and D, we're getting faster and faster. So B is faster, C is faster, D is a little faster, so our speed is increasing like this. Now that means that on our position, we're going to start at a certain distance away. We're going to slowly get faster and go a certain distance. But you're going to start to have this curve here because you're going faster and faster. As time goes on, you're going to get further and further away faster. And so that's another drawing of motion and velocity where the velocity is actually getting faster and faster. Okay, now I would like to show you guys some other ways that velocity might be asked about. So like for example, you might have a time and a position chart. So over these 4 seconds, you're 0, 5, 12, and 17 feet away from where you started. So if you want to know the average velocity from t equals 2 to t equals 4, this is actually probably an easier way to calculate it. They want from 2 to 4, and they give you an x and a t. So remember, velocity is change in x over change in t. The change in x here would be 17 minus 5. And the change in t would be 4 minus 2. Or you could just think 12 over 2, which would be 6 meters per second. Okay. Now, a note here that I haven't been very clear about is the reason I say meters per second here is because you are always taking a distance dividing by time for velocity. So miles per hour would be a velocity, or meters per second would be a velocity, and so on. So we have another more involved example here to look at too. Alright. Okay, a biker travels for 5 meters per second for about 2 minutes. She stops at a light for 1 minute, and then goes 6 meters per second for 30 seconds. So we want to know, what is the total displacement? Alright, so I'm going to draw a picture of what this will kind of look like. Just a rough sketch. A bike is it's going 5 meters per second for 2 minutes. So if we're looking at displacement here, for 120 seconds, he's going to be traveling 5 meters every second. So it's going to look like this. She is going to be that far away from where they started. Now, if you do the math, that would be 2 minutes is 120 seconds times 5 meters every one of those seconds. This means this person is 600 meters away at 120 seconds. Now they stop at a light for a minute. So from 120 to 180, there is absolutely no displacement. They will remain at 600 meters away. Let me make that a little easier to see. And then for 30 seconds, so up to 210, They travel 6 meters a second. Now, 6 meters a second, if you do 6 times 30, that would give you 180 displacement. But we are already at 600 meters. And so this total displacement here would be an additional 180 plus the 600, so it would be 780. So for the total displacement, we did it in pieces. We figured out how far would she have traveled in each time period, and we found 780 meters. Okay. A follow-up question here is, what is the average velocity? So we do velocity equals change in position over change in time, displacement over time. Now we know total that she went 780 meters. The total time is 210 seconds. So 780 divided by 210, that would be, I will write 3.7, since it appears that we have 2 sig figs. Sorry, this should have been 6.0 meters per second, because that would make it 2 sig figs. Excuse me. Now it's 3.7 meters per second. So you might be saying, wait a second. She was traveling 5 meters a second the whole time, and then 6 meters a second in that last part. Well, the average then is brought down because there is this period here where there is no velocity whatsoever, so it brings the average down. So this is another case where the average velocity is changed a little bit because of what was happening in between. So the last follow-up question might be, C, what would the velocity be if there was no stop? Okay, well, the change in x would be the same. The change in the displacement still would be 780, but the change in time would be different because we'd remove that 60 seconds of dead time. And so we would actually have 150 total seconds. And so 780 minus 150, whoops, I'm sorry, 780 divided by 150 would be 5.2 meters a second. Now that average velocity makes a little more sense because without a stop, you would be somewhere between 5 and 6 meters per second. And because we were 5 meters per second for much longer, it's going to be closer to 5. And so when you see problems like this, you're going to have to kind of break it up into pieces and figure things out using the rates over those little pieces.